Okay, so we started recording. Today, let's go over CCA encryption from Diffie-Hellman and random oracles from any CPA encryption and non-interactive zero knowledge. And eventually, we would like to do it from Diffie-Hellman in the standard model, so without RO, and without non-interactive zero knowledge. So, in particular, we don't know efficient instantiation of this together with appropriate CPA encryption, except for RO. But that doesn't help because we already know even faster schemes with RO. So this is Naor Jung, and then Dwork Naor. This is so-called the HIES construction. Also by Bellare et al. There is also Fujisaki Okamoto. So maybe we'll mention it briefly. Alternative construction, and in the standard model, this is Kramer-Schoup. Okay. So let's take these things one by one. Computational Diffie-Hellman and random oracle imply CCA secure KEM. So this is stands for key encapsulation mechanism. Under so-called Gap Diffie-Hellman assumption. So this is actually Gap Gap-CDH assumption. Okay, so let's take these things one by one, and so that's one thing, and then CCA secure KEM plus CCA secure symmetric encryption give you CCA public key encryption. So here I mean public key. Public key encryption. This is so-called hybrid encryption scheme. Okay. Let's see. So first thing, what is KEM? So this is like public key encryption for keys, not general messages. So it is motivated precisely by this usage of in the hybrid encryption. So let's say first so in other words, the only thing we care to encrypt are random keys. We don't care to encrypt general messages. Okay, so in other words, KEM is a triple of algorithms: key generation, encrypt, or sometimes called encapsulate, and decrypt, which work like this: key generation on security parameter outputs secret key public key pair. Encapsulate just takes the public key as an input. And because you don't care to encrypt a general message, you just want an encryption of a random key. So the encapsulate algorithm outputs a ciphertext and a key, such that K is a random bit string of length of the appropriate length, and C is the ciphertext that encrypts it. So decryption under the secret key of the ciphertext gives you back the key, right? And the correctness is that for every secret key, public key, of course, for every security parameter, for every secret public key generated. Okay, so for every security parameter, if ciphertext key is an output of the encapsulation, then the same key will be returned by the decapsulation or decryption of the ciphertext. Okay, and what about security? So this is the CCA Attack Security. For every efficient algorithms A, probability B prime is B in the following game is negligible. Okay, so what's the security game? You pick the public keys. Oh, this is hard to read, right?
Yeah, a bit, but I can understand.
Let me try to refocus.
Isn't there a setting to fix the focus? I think the problem is that the camera is trying to improve things and it's not working.
Yeah, that's better.
Oh,
right?
now it's good. Now it's good. Yeah.
Right. So when it defocuses, just say that fix the focus, because
okay.
Sometimes. Okay, thanks. Okay, so secret key public key is generated by the key generation. Attacker gets the public key, and the also the encapsulation algorithm is executed, and then there is a key which is assigned to be either key K if bit is 0. So the whole thing picks a bit at random. It's a challenge bit. It's like the bit that determines whether we will encrypt M0 or M1 in the standard encryption game. And the key prime is either assigned to be the real key when this bit is 1, or it's random if the bit is 0. And the attacker hold on a second. I'm looking for an eraser. I don't see it. So the attacker gets the public key, the ciphertext, and this key, K prime, which is either real, which is either the decryption of the key that is encrypted in C, or it's a random string. And the attacker can query decapsulation oracle on arbitrary ciphertext as long as they're different from the challenge ciphertext. And the decapsulation oracle just gives back presumably K prime, which is the decapsulation of this C prime, right? So and this adversary can repeat any number of times it wants. And finally, adversary outputs a bit B prime, right? So in other words, this is like the standard semantic security of encryption game, except there are no messages. And so therefore, this challenge ciphertext can be generated straight away together with the public key. And the game, the goal of the adversary is to determine whether it is given to distinguish the key, the real key from a random key that is encrypted in the challenge ciphertext. And it's chosen ciphertext secure if he cannot determine this, even though for any other ciphertext he can learn what the key is behind any, and what is the key encrypted in any other ciphertext than the challenge one. Okay. So how is this used? Well, here's the hybrid encryption, which is how standard public key encryption is essentially always implemented. Okay, it's like this: if if E is a KEM, and let's call it with epsilon is a symmetric. So this is for the Zambigu, to the Zambigu is a public key KEM. You can also think of symmetric key KEMs, but this is the standard usage is for public key. It's a symmetric encryption, epsilon. Then E prime, which takes a public key and a message and outputs two ciphertexts, C and C bar, where C and Cca are generated by the KEM encryption, so E on PK, and C hat is generated using the symmetric key encryption, using the resulting key and the message, right? Is a public key encryption scheme, right? Because the KEM generates key, is capable of creating encryptions of random keys. So that's what we use KEM for. And then we feed this, then we encrypt the actual message with the symmetric key encryption and the key K. How do we decrypt? Well, when you get C and C hat, first you decapsulate C using the secret key to get the key K. By correctness, it's the same one. And then you run the symmetric key decryption to C hat to get M back, right? And a theorem is that if both E and epsilon hat are CCA secure, then so is E prime. Okay, so this is a CCA secure KEM, this is a CCA secure symmetric encryption, and this is a CCA secure public key encryption. And the proof is not hard, it's in the Katz-Lindell. It's there's not so much happening here. So it's a standard proof by games where we modify the security game of the public key encryption piece by piece by replacing either at different game moves, either the action of the KEM or the action of the symmetric encryption piece by piece and arguing, like for example, for symmetric encryption, we change encryption of M to an encryption of, let's say, constant or a random string, and argue that the security goes by security of symmetric encryption, or we change the KEM part so that instead of using the key K, we use instead a random key in feed the symmetric encryption with a random key. And if adversary can tell a difference, then he basically breaks the KEM security, right? So these are standard reductions, and they are shown here. It's not a learn. Okay, so this is how people use public key encryption, both in the case of RSA and in the case of ElGamal-like encryptions. So security-wise, therefore, it's sufficient to look at the security of the KEM inquiry, which has a slightly simpler formulation, and perhaps it's slightly simpler to argue and construct. Any questions?
Okay, so the idea of KEM is that usually you have access to the encapsulation, even if you don't have the secret key, correct?
No, say it again.
So the secret key in the KEM scheme is just to decapsulate. So if you get C, you won't be able to find the key without the secret key, correct?
Yes, it's just like an encryption.
Right.
The
No,
only difference is that you don't encrypt messages. You output this.
Right.
Basically, what this does is that it picks a random message and encrypts only that random message. Okay, but other than that, it's like an encryption.
Right. It's just the fact that the key appears there. Like the encryption gives you the key too, right?
Right. So
the encapsulation.
In the encryption algorithm, but think of this key K as the message, as the, the encrypted message, right? So rather than having an input, an arbitrary message into encryption, the encryption picks a random message and encrypts that. And that's basically, okay, well, it's a syntactic constraint on standard encryption. Other than that, everything is exactly the same.
Right, but is there any reason in all this we did for K to appear there? Couldn't we just hide the key even in the encryption part, encapsulation part? We didn't.
Well, I mean, then how would you use it? Right? You use, say, the encryptor. He needs to encrypt a large message.
You could decrypt it. You could, if you have the secret key, you could
you don't.
find key.
So this is a public key encryption. A public key encryption has a public key and a message, and you need to encrypt the message. So it's.
Oh, now I see.
Yeah.
Okay.
Right. So this is indeed a typical usage of public key encryption. We don't, unless we have some very particular application where encrypted messages happen to be very short. What we typically do is that we take a message which is long, and we use the public key encryption only to encrypt some random key, and then we use that key in a symmetric encryption to encrypt the long message. Because this is fast, right? And this is slow. So we don't want to redo public key encryption to encrypt chunks of the message, right? We just apply it to something whose length is only a security parameter, and then we hook that short thing in a orders of magnitude faster symmetric encryption to only this part depends on how many blocks you encrypt. This part does not. Right? And this is the public key operation, right? Which is typically 3 or 4 orders of magnitude slower than this guy.
Okay, thank you.
Okay, so okay, so here is the DH based KEM, and an incredibly assuming RO hash. So G generates a prime order group order, let's say P. The secret key is X, which is generated at random in the group order. Public key is Y, G to the X. And KEM on Y picks a random R in the group order and outputs C, which is G to the R, and key K, which is hash of Y to the R. That's it. And so what do we need of this hash? Hash is a hash that takes any elements in group G, generated by group G, and outputs that string of length security parameter. Okay. And now how does the decapsulation, sorry, so this I called, so this is a KEM, so this is a KEM key generation. This is KEM encapsulation, and here is the KEM decapsulation. Uses secret key X and ciphertext C, and it outputs hash of C to the X. And you can see, right, that this is this is a Diffie-Hellman, right? G exponentiated to R is C. Exponentiated to X is Y. And the encryptor uses the public key. So this is the public key, and this is the ciphertext. And this is the secret key. And the encryptor uses the randomness, encryption randomness, to generate a ciphertext and to generate this key material, which is Y to the R. But the decryptor can regenerate the same thing by using the secret key, right? So this is these two moves are used in encryption or encryption encapsulation. This one is a key generation, and this one is decryption, right? And it creates the same key. Okay, so I'm just going over Diffie-Hellman yet again, and they hash, both of them hash it. Okay, both in encryption and in decryption. Okay, so it's clearly correct. What about theorem or claim? This DH-based DH plus RO based KEM is CCA secure. Okay, this, let's call it hashed Diffie-Hellman. KEM is CCA secure in random oracle model for the hash function. Okay, and using the scam in hybrid encryption, it's the so-called DHIES public key encryption. This construction has a name. Okay. So okay, let's see this proof. So let's see what the attacker gets here, right? So attacker gets y value, which is G to the X, and it gets a ciphertext, G to the R, and it gets a random a string K prime. So X and R are picked both in ZP. Okay, so this is now we are sketching the proof. Because what does the attacker get in a KEM scheme, right? So he gets a public key, so this is G to the X. He gets a ciphertext, this is the G to the R, and he gets a random string, which is either the right key or a random. Okay, so K prime is either hash of the right thing is the decapsulation is G, the ciphertext to the X, so it's G to the XR if the challenge bit is 1, or a random split string if the challenge bit is 0. The attacker's goal is to predict this bit to distinguish these two cases. And what does attacker have at its service? So it has the decapsulation oracle. So it's an oracle that has this private key. It's getting some ciphertext which cannot equal to this one. And what does it give back? Well, it gets back. Let's change. Okay, let's change the notation somewhat. Let's call it K hat. Okay. I will change it here for okay. All right. No, okay, sorry. This was wrong. I wish I had a working. Oh no, this is horrid. Hold on a second. This was in G prime, and this was K prime. That's precisely why I want to distinguish these top level parameters from these ones. Okay. So there is this K hat or K bar, right, which is the challenge, and here are the decryption queries. And what does he get from decryption? He gets a K prime, which is the hash of C prime to the X. Right, that's what you get. Also, we are in the random oracle model. So the attacker also can ask hash queries what's the good, let's call these hash queries Z. And you know what? Let me call this ciphertext C hat, C bar. And this will allow me a slightly easier notation here. So this is not C prime, but simply C. Okay. Okay, so I designate these parameters with this, the challenge with bars, and that we can simplify my notation here for the stuff that it repeats. So attacker can also hash, and well, and he gets back well, hash of Z. So let's see what is it's slightly differently now. Just see that. What is the challenge key string, which is either real or random, is a hash of the Diffie-Hellman solution on these challenge points Y and C bar, right? So observe that attacker cannot tell K real or random unless A queries H on the value V hat, which is the Diffie-Hellman function of the inputs, the public key and the challenge KEM ciphertext, right? Because this is this is G to the XR. So formally, we can say, let's call an event query an event that queries H on Z equal to G to the XR. And let's first argue that unless he makes this query, then he has zero probability. I mean, there is his view is identical. Is independent of bit B, because if H is a random oracle, and everything you see is independent of this query, then you have no idea like what the H outputs is, right? Because H is a random function. So let's see that, but H is not just queried here, it's also queried here. So this guy makes queries to H. So perhaps G to the XR has been used in the game even if attacker doesn't send Z to the hash oracle. Namely, perhaps DX at some point makes this G to the XR query. But it's immediate to observe that it does not, right? Because this value DX never queries H on G to the XR, because if C to the X was equal to C bar to the X equal GXR, then C would be equal to C hat. Okay, because it's a cyclic prime order group. So every element is a generator, and so this equality implies this equality. Okay, there's no small order subgroups that can make this. Well, as long as x is not equal to 0, that's the only case, right? And this happens with negligible probability. Okay. Okay. So that's so. So this implies that if advantage of A, which is the probability B prime equals B minus the guessing probability, is non-negligible, then event query defined as A queries H on G to the XR must be non-negligible as well. Okay. So now we have a system where A gets Diffie-Hellman challenge, gets to query this decryption, gets to query the hash, and at some point must query H on G to the XR. Well, if he does, then perhaps we can guess where which of these polynomial many queries have contains this, and simply the reduction given this Diffie-Hellman challenge is going to guess one of these, and it will be equal to that, and it will solve the Diffie-Hellman problem. Oh, sorry. So the hashed. Okay, sorry, I forgot to spell out what is the assumption here. Under a so-called Gap-CDH assumption, this hash Diffie-Hellman KEM, right? So we haven't yet said what a Gap-CDH is, but I'm leading to it. So let's say that we want to prove security based on CDH. We get the reduction gets the CDH challenge, and it seems to be able to, from one of the hash queries, extract the CDH solution. However, the problem is here, obviously, right? Like the adversary also queries the decryption, and this oracle needs to have the private key. The reduction, which gets the Diffie-Hellman challenge, cannot know the discrete logs of the challenge, or otherwise. Yeah. Okay. So the reduction would have to like internally break the discrete logarithm, which would fail to make a proof of security, right? The reduction has to just use attacker to solve the challenge. But here's the thing. If H is a random oracle, then perhaps the reduction can output random points here, and as these hashes. And how can adversary tell whether the random points returned by the reduction R equal to H of the Diffie-Hellman of the proper Diffie-Hellman value, or not? Well, the only way to tell is to hash this preimage. So the adversary would have to, let's say reduction just returns random capital K values as decryption outputs. How could adversary tell that the reduction is divergent from the real security gain? It would only tell this if it queries Z equals Cx to the hash. But perhaps the reduction could given adversaries, given C and Cx, perhaps the only thing that the reduction would have to do is to identify the proper C-Cx pairs and just make sure that this hash is answered in the case C and Cx, C and Z are in the proper relation, namely Z is C to the X, then at that point, the reduction would make H output the same value that it output here. So adversary makes many of these. So there is many Cs, C1, C2, C3. It's like a big table of Cs and capital Ks, which were answered as presumed decryptions, quote unquote, right? Simulated decryptions. Here, there is a whole table of different Zs, Zis, and different hashes and the hash values on them. If the reduction operates these two oracles could match Cis with Zjs and just detect, if it could detect that for some I, Ci and some Zj, it holds that Dj is Ci to the X, then it could make consistent answers. And for all others, it can, for all Cis for which there is no Zj in a proper relation, and for every Zj for which there is no Ci in the proper relation, it's free to answer both of these at random because they correspond to different hash values, to hash on different inputs. And because H is a random oracle, we don't care, right? They can be answered at random. So that means that what the reduction has to do to survive this this way of simulation is it doesn't really have to compute C to the X for any C that adversary presents. It only has to identify the correct C to the X values that are explicitly specified by the adversary in these hash queries. So rather than compute, it has to just recognize. And that's exactly this Gap-CDH assumption. It's an assumption that an algorithm, that the Diffie-Hellman problem, namely having G to the GX and G to the R as inputs, it is hard to compute G to the XR, remains hard even if you had an oracle which identifies proper Diffie-Hellman input and output pairs. Because this reduction would just need to have access to such an oracle to survive. Okay, so let's spell out what this assumption is, and maybe say a few words why on earth this assumption makes even a remote sense. So this is the Gap-CDH assumption. The assumption is that for every efficient algorithms, and the assumption is in group G, polynomial in length of group description. So, okay, this could be an elliptic curve group. It can be a group of prime residues, and other settings are possible as well. Let's the probability that A who has access to decisional Diffie-Hellman oracle in group G, and the inputs of A are G to the X, G to the R, and he needs to compute G to the X R, that this is negligible, where CCA oracle is takes 3 inputs, X, Y, and Z, and it outputs 1 if, you know what, it's easier to write it this way. The Diffie-Hellman decisional Diffie-Hellman oracle takes 3 inputs: G to the A, G to the B, G to the C. Okay, so these are arbitrary elements in the group, and it outputs 1 if C is A times B, and 0 otherwise. Okay, so the decisional Diffie-Hellman oracle, just given a Diffie-Hellman input-output pair, it tells you whether it's the correct one or not. So in other words, this decisional Diffie-Hellman given X, Y, and Z outputs 1 if Z is the Diffie-Hellman function on X and Y, and 0 otherwise. So rather than computing the Diffie-Hellman function, the CCA oracle just tells you yes, no, if you provide the Diffie-Hellman function output. Now, why this is so? Groups, elliptic curve groups with bilinear map implement the CCH oracle. Okay. Why? So a bilinear map is a map on the group to some target group, which is bilinear in the following way: that if you give it G to the A and G to the B, it is the same as G to A times B. Okay, and this immediately gives the decisional Diffie-Hellman oracle, because CCH on XYZ can be implemented as you output 1 if the bilinear map on G and Z is the same as bilinear map of X and Y. Right, Y and 0 otherwise, because this is equal to E of G. So G to the A, G to the B, G to the C, and the G to the A times B. Right. So this is G to the C. So this is let's call the generator of the target group as a bilinear map applied to the generator of the base group. So this is G to the P to the C, and this thing is E of Ga GB, so it's generator of the target group to AB, right? And if they are equal, then these things are equal. So therefore, Z is the solution to the Diffie-Hellman challenge on X and Y. Okay, and basically all cryptography on elliptic curves with bilinear maps.
The paper is a bit too low.
Oh, yes. Is based on either discrete log or Diffie-Hellman hardness in such groups. And DL in such group is basically called a gap DL, and Diffie-Hellman is a gap Diffie-Hellman, so computational Diffie-Hellman. Note that decisional Diffie-Hellman in such group doesn't hold, right? So distinguishing, because this oracle is precisely deciding the decisional Diffie-Hellman problem. It's able to tell the Diffie-Hellman tuple efficiently by just, sorry, this is a typo. It is not a G, but a bilinear map E. So, well, this is not, of course, a proof that this assumption holds, right? It's as old as no, that's why it's called an assumption and not a fact. But if this assumption was broken, then essentially all crypto using this setting would go down. Another thing, so why? Okay, why? But another way to gather at least some evidence for the hardness of an assumption is that in so-called generic groups, where the only operations we have is multiplication of group elements, then it's rather easy to see that if the only efficient algorithm can basically multiply group elements, and what that translates to is adding the exponents, right? Because it's still cyclic groups. So when group elements are multiplied, you effectively add this is called representation of the group element in this group based some generator. And because efficiently you can effectively only add the hidden discrete logs, well, that's first of all why computing this multiplication of two of the discrete logs of two challenges is hard, and the generic algorithms that do that are square root of the group size, like the Shank's algorithm, baby step, giant step. But given an access to an oracle that can tell you whether two discrete logs are in the multiplicative relation, okay, so you give it the three group elements and you test whether the multiplicative relation is correct or not. Basically, it's not helpful. The only ones for which this test is going to likely say yes are the ones that you have explicitly computed to make sure that they are in that their exponents are in multiplicative relation. For all others, the probability that they are is negligible in the order of the group. So basically, this oracle in the generic group is useless. And so that's why these assumptions still hold, right? In particular, generic algorithms cannot make use of this oracle. Hold on, let me close the window. Okay. So now let's see that that the reduction that we wanted is going to be right. Is going to be helped by this oracle, by this assumption.
Professor.
Yes,
so
yes.
is there any characterization of these general groups you said? Because every cyclic group of order P will be ZP. So is there some family of primes that is particularly good, or we just don't know?
ZP is not a cyclic group of order P.
ZP?
ZP is oh, okay, yes. So ZP is an additive group.
Yes,
sure.
But like every group would be isomorphic to it, right? If you have order P, it must be ZP.
Yes, it will be isomorphic to it.
So is there any characterization of which primes would like be good for this idea of CCA not gaining anything?
So,
or maybe a better question would be: is there some primes that definitely are not good?
You mean as orders of group?
Yes. Like, is there any characterization of which ZPs would be good in this regard?
So ZP, okay, I don't want to say ZP because that's it's an additive group, and all the problems are based on hardness of discrete logarithm. So you need to okay, but if you want to think of this additively, fine. So for example, that's a natural notation for elliptic curve groups. Actually, the group operation is called addition of group elements. And but yes, so generic group arguments work like this. So think that you have an additive group as you want, DP. However, the representation of group elements are like some bit strings that give you no information about which group elements they really represent. So
right, because the generator wouldn't be one; it would be something else.
Right. So
yes, I see what you're saying.
What you get is I times the generator. Yes, and the discrete logarithm assumption is that given the random I times generator, you don't know what an I is. Now, for the elements that you created yourself, you can take a generator and you can multiply it by any integer, right? So then, of course, you know what those integers are. But a group is generic if that's the only action you have. So the only action is that you can take a generator, create group elements, and by the way, and any challenge group elements that you have, well, you can add them and you can multiply them therefore by constants, and you can combine. So you can take a generator and a challenge group elements and add any multiple of one and the other to each other, right? And create a linear combination of them. And then the only other operation is that you can test for equality. So if you happen to create two group elements using different process that equal, that's exactly how baby step, giant step algorithm. It creates two different group tables of different group elements, and it has a discrete logarithm attack if it finds two entries in one table and the other which equal. Because basically for these two tables, which are either tables of elements created using so-called giant steps and table of elements created using the baby steps, if there is equality, then algorithm found two ways to arrive at the same linear combination at the same value, and that gives a solution to the discrete log problem. But that algorithm, if the group elements are really, so the representation of group elements really are oblique, like think of them as pseudorandom strings, and they don't give any information about the underlying object, then you can easily see that the bound on any algorithm is square root into group size. But that doesn't allow you to characterize like anything about the primes. You know, these characterizations of like which primes are good, which curves are good, they are subject to specific instantiations of these groups, where other precisely non-generic algorithms have some, you know, discover some weaknesses in discrete logarithm over these groups. So
right,
that's so the general number field sieve exactly, you know, basically uses other like factorization of p-1, for example. But that's for prime residue groups. Over elliptic curves, you have other sets of concerns and some, you know, weak parameters.
I think my point is then that if we know some attack on some group of order P, say elliptic curve, and we knew an isomorphism to another of order P, then the attack is the same still. The problem is, of course, finding isomorphism. Yeah, I think I understand now. Thank you.
Right. Okay. Okay. So let's finish up with this reduction here. So this was our motivating setting for introducing this assumption. And let's now show a reduction, right? So it gets two elements where it gets a group, elements like this, where yc hat is g to the x and g to the r for random x and r. And its aim, of course, is to compute the answer g to the xr, right? That's what it wants. But it will use this Diffie-Hellman oracle. And let's see how it can use it. How did we want to use it? So we wanted to basically tell whether some CZ pair is correct. What does it mean? So if so, the intuition was that all A gets from DX and H queries is either independently random outputs, unless Ci and Zj are correlated by that Zj is Ci to the X. And in that case, the response of the DX oracle on Ci has to be equal to the response of the hash oracle on Zj, right? Other than that, this seems like the DX and H can output random values, and we should be indistinguishable, or in fact, information theoretic identical to the view A gets in the real game. So the reduction needs to be able to test whether these pairs are okay. So what does it give to the Diffie-Hellman oracle? It gives him Y, which determines the DX. It gives him Ci, and it gives him a Zj. And it just needs to know whether these are 1 if basically Zj is Ci to the X, right? Because Y is G to the X, and 0 otherwise. So let's see how the reduction can use that to emulate. Well, it will pick this key at random, and it will send to the attacker past the YC hat K hat to the attacker. When attacker asks for decryption, decapsulation of any ciphertext different from the ciphertext challenge, the reduction does this, checks if GK on C set before. And obviously, when it was set, just answer the same thing. Otherwise, check if, so this reduction is going to initialize by creating 2 empty tables, the table for the decryption queries and table for the hash queries. That there exists any entry ZJ, sorry, ZH in the table for the hash function query. So intuitively, the hash function, the TH, is going to keep table pairs Z that was inputted and the H that was outputted. So the input TH stores input-output pairs so far manipulated, processed by the hash during the hash queries. And the TD decapsulation table will keep the C capital K pairs of input outputs in the to the decapsulation queries. Okay, so check if there was a ZH query in pair input output pair in the hash table, such that DDH on public key Y, this query C, and this value Z is 1. If so, set K to H. Otherwise, set K to random value and store C capital K in the table for decryption queries. Okay, and that's how you answer key K. Right, so this is the decryption oracle, okay, which does not know X, reduction does not know it, but that's how it's going to simulate this oracle. Now let's see what happens when how do we process the hash queries? So the H oracle is going to do this. First, checks if H sorry, the input to H were called Z's. H of Z was set before, and of course, if it was, then just answer it. So here you use the TG table, right? The TG table stores input outputs of the decryption queries. And here we'll use the TH table. Okay, if it was not, then again, now check if there exists, to keep consistency, the CK entry in the decryption table, such that, again, we check for the same relation. If so, set the value H to be this capital K, and otherwise set H at random, and store this EH in the table for the hash, and that's how you enter out. That's how you that's the hash value that you return, right? So this is the H oracle simulation. So the view of A, or A's view in interaction with R is identical to A's view in interaction with CCA experiment, CCA KEM experiment, unless event query happens. Okay, because the only distinction is that in the reduction, this was just set to be a random value, whereas here it was an output of the hash if bit is 1, and it was random if bit is 0. Okay. So the decryption is completely consistent with the way the decryption works, and the hashing is completely consistent, and this is so over the random choices of H, right? The H view in interaction is an interaction with the security game and hash function H. And so it is in the reduction. Actually, I should this hash function only plays a role in CCA game for random H, right? So in the real world, H is a random function. In the simulation, in the reduction, H is manipulated by the reduction. And it is manipulated in this way, right? Like where values are either assigned at random or they are checked from the other table, but when they were inputted in the other table, they were also inputted at random. So therefore, the total view of H here is recreates a random function. Okay. Indeed, as in the case of the signature schemes last time, the FDH signature scheme, a random function plays the role of the universal trapdoor. I mean, of like not universal, but of a very large, it's really a family of trapdoors where for every query you can, you in a trapdoor way, you can process these queries by the reduction, in this case, checking some external relationship and correlating the way it answers, right? So we have identical view unless this event happens. But if event query happens, then R can catch it. And
could you move the paper a bit?
Yeah. And solve the CDH challenge. So what does R do in addition? It has to basically detect that some of these Z's perhaps are this. So for every Z queried to H, R also checks if the DDH G on the challenge perhaps is 1. And if so, query happened. But R outputs Z and breaks the Gap-CDH assumption. So it's an example of a reduction where the view is imperfect. There is some event where where the reduction and the security game can be distinguished. But that is exactly the event which allows the reduction to solve the challenge. So the only way for A to tell the difference between reduction and security game is to create something that at that point makes the reduction solve the problem. So it's until the event happens, the view is the same, and therefore formally the argument is like this: until this event, the view of adversary in the reduction is the same as in the security game. Therefore, the probability that the query event happens in the reduction and in the security game are identical. Okay, this very argument implies that the probability of query in the security in the reduction is the same as the probability of query in a security game. So, and we argued here that the probability of query in the security game must be non-negligible if attacker breaks the system, right? So therefore, it must be just as non-negligible in the reduction, and that means that when it happens, the reduction will solve the Hammond challenge. So, it is similar in a sense to this trickery with random operators that we've seen in the case of the FDH, right? Reduction plays double role of manipulating the oracle here, and it uses the hash function in order to quote unquote decrypt, but it doesn't stop the reduction from solving the problem if right, this ability does not destroy the extraction of the Diffie-Hellman challenge, solution to the Diffie-Hellman challenge from adversarial behavior, which, you know, in this case of encryption, makes the bit correlated with the challenge. In the case of in signature, this was the extraction happened from the forgery, eventual forgery of the adversary against the signature scheme. You know, as is the case of the signature schemes, you can wonder how you can assure this in a standard model, this ability to pass the decryption queries and yet extract a solution to a challenge from an adversary that breaks encryption, and that's of course well, the next on the program. Do you have some questions to? Oh, hello.
Hello, I can hear you.
Oh, okay. So if you don't have questions to the reduction, then we can end now, right?
Yeah, I think I'm all right.
Okay. All right. Okay. So, see you next time, and I'll post. Katz Lindell has a. Well, no, they actually have exactly this proof. So this, they have this proof for the case of RSA, which is very, very similar. So I will spell this out on the syllabus.
Okay, thank you.
Okay, thanks. See you next time.
All right, see you.